Okay, good morning. Let's get started. My name is Hanno. I have been a Java developer since 2003, and one of the subjects that has always interested me is concurrency. So that's why I want to talk to you about concurrency this morning, how Java's concurrency all started in the 90s, how the support for concurrency improved over time, what features have been added in the meantime, and of course also what is happening with concurrency in the current releases and the future releases. Now the idea for this talk actually came to me on a Friday night while I was not working. I was out for a few drinks with some friends. I think the best idea is always come when we're not stressed out, right? And so I was there at a bar hanging out with a few friends just in a relaxed mood, and the waiter came up to us and said, "Hey, can I get you something to drink this evening?" And we said, "Sure, what do you have in stock today?" And he didn't give us a menu or something, he just started listing all the drinks he had on offer, right? And do you recognize that feeling when a waiter starts listing all these options, and by the time he gets to the 10th item, you're like, I already know what I want, but I'm going to let him keep talking. Right? And then he gets to the 20th item and the 25th item. And then he stopped and he said, "So what will it be?" And we were like, "What was the first one again?" Right? So he was so frustrated because we let him do all this work. And he discovered, of course, that it wasn't really necessary. This is exactly a situation where the new Java feature of structured concurrency could have solved the problem. When you've got a successful result in the first few attempts, then you could easily cancel the rest of the work. I'll get back to this example when we get to structured concurrency and the shutdown on success strategy. So bear with me as I lay a bit of groundwork regarding the Java history of concurrency. So if Java's concurrency features and the way that they made their way into the programming language, if we compare them to a train journey, that means that we have to look at a few past past train stations, right? So what stations have we had so far? What is the current station that we're now on? And what stations will we still get in the future? I also like the bar analogy a lot for our examples, so let's extend it a bit and assume that the bar also has a restaurant attached to it, right? And I'm going to demonstrate all concurrency features with this restaurant example. But the restaurant that we're dealing with today is not the best restaurant, right? A lot of things go wrong here. Kind of like the restaurant where this image comes from. Any Sesame Street fans, people who grew up with it? About half of the room, that's good, that's good. So Sesame Street fans, I'm worried that, if I do this talk for a few more years, the number of hands will get less and less because we're entering into the Netflix generation. But still, some Sesame Street fans around. This was, by the way, hand-drawn by my wife. She's far better at drawing than I am. I guess opposites attract, right? But I'm thankful for this example. So in this sketch in Sesame Street, Grover is the waiter, and the blue guy there, Mr. Johnson, he orders stuff. And obviously he didn't order a Lego brick, but that's what he got served anyway. So stuff like this goes wrong all the time. And in our code examples today, also a lot of things are going wrong. And they have to do with concurrency. So imagine that we want to model this restaurant of the Sesame Street sketch. We could create an interface we call restaurant and define a single method we call announce menu. And that means that the restaurant can announce the menu for today. And the restaurant that we're modeling is always serving a 3-course meal, a starter, a main, and a dessert course. Well, if we would implement this using Java's classic threads, we would end up with probably something like this, meaning that we should create threads here at the top. And in this case, we've created subclasses of threads so that it can hold state. Then we start up the threads, and we call join on each of them. So we wait for the end result there, and after all joins have completed, we can reconstruct a new multi-course meal. And what we're doing here, we're storing the announced course in the thread subclass. This is like the pre-Java 1.5 approach, because we didn't have callables back then, so we had to store any result that we ran in a thread in its state, like we did up here in the announced course field. So It's a pro, I guess, that we can do multiple things at the same time with threads, but the drawbacks, we cannot return a value directly because callables were not yet supported pre-Java 1.5. And one of the major drawbacks, in my opinion, is that the workload and the mechanism that we run it on are one and the same. So the task that we have defined and the fact that it runs on a separate thread is very tightly coupled. There's no way for us to release them from each other and configure them separately. But of course, we can introduce something more sophisticated. Starting from Java 5, ExecutorService was introduced, and the code example that is on the slide right now could then be reduced to this. I'll walk you through it line by line. So here, this is the place where we create our executor service, and we can configure here the number of threads that we want to use. So in this case, using 3 threads, but we could easily change it to use more or less. Then we submit 3 announced course tasks here, and they return futures, which is Java's abstraction for a result that gets available later. And then finally, we call get on these futures here that will eventually yield us 3 results, and it will allow us to construct a multi-course meal. So that looks quite good to me. I mean, we are able to separately define the unit of work and the task at hand, though there are still a few problems with this code. So imagine after we went to the bar and we annoyed that waiter, we sat down at the table and asked for the menu of this evening. And this restaurant has a certain problem, and that is that for every ingredient that they need to create a meal, there's a 5% chance that the ingredient is not in stock. That is what we have modeled in our code. I'll show it later to you. So that means that if the chef picks a certain starter course, but one of the ingredients is out of stock, then it doesn't really make sense to announce the starter course. In fact, you might even want to ask your guests, do you still want to stay? Or I could understand if you want to find a place somewhere else where they do have starter courses. And if we process this into our code example, that means that all of the announced course methods that are here on line 10 to 12 can throw exceptions now. So imagine there is an out-of-stock exception, and if one of the announced course methods throws it, we can no longer construct a valid instance of multi-course meal. And these are, there are great consequences for our code here. For example, let's look at line 10. If our waiter, who is called Zoe, if she announces the main course, but this takes a long time, right, before she's done, before the future gets returned back, then what happens if line 9 fails in the meantime? If announced course starter by the waiter Grover fails because there's an ingredient missing, then the entire announce menu method will wait unnecessarily for the main course announcement because it's blocking here on line 13 on main.get. But the sensible thing to do was to cancel the entire thing because we already know that the starter course announcement is not going to work. Similarly, different problem, if an exception happens on this line, then it will be thrown by main.get on line 13, but the invocation on line 9, announce course by the waiter Grover, will continue to run even after the exception has been thrown. And to zoom out a bit, if let's assume the main thread is running this entire method, announce course. If this thread is interrupted, then this interruption will not propagate to the subtasks. So all 3 threads that have been spawned will still continue to run until they're done with their work. So we've got thread leakage here. Ultimately, our problem is that our program is logically structured with task-subtask relationships. But these relationships only exist in our minds, in the mind of the developer. The Java executor service construct is not ready for this pattern of unstructured concurrency. So let's summarize here. The task can directly return a value, so that's good compared to classic threads. and we have separated the workload and the run mechanism. But the drawbacks are that executor service will wait for all tasks to terminate. And like we saw earlier, it allows unrestricted patterns of concurrency. It doesn't enforce any task structure. So in theory, one thread could create an executor service, and a second thread could submit work to it. And the threads that actually execute the work would have no relationship whatsoever to either the first or the second thread. So is there still someone in the room who remembers the classic programming language BASIC, or has dabbled with it a few times? That's good to see. Then those people, and perhaps the rest also, will recognize the go-to statement, right? Go to 020, go to 040. A very notorious construct of the basic programming language. And I'm bringing it up because goto is a one-way jump. You jump from line 020 to line 080, but you have no guarantee that you will ever return to line 020 or the next line, for that matter. And spawning threads from an executor service, you can kind of compare to doing a one-way jump to execute a goto statement. They're like the concurrent equivalent of it. There's a jump to somewhere else, you're losing the control, and you don't know when it will return. So this is what I mean when I say that executor service allows unrestricted patterns of concurrency. Okay, moving on in our concurrency journey, ThreadLocals. ThreadLocals have been in place in Java since Java 1.2, and it's an elegant way to model a variable that is unique to its thread. So that means that if you declare a variable ThreadLocal, then each thread will have its own independently initialized copy of the variable. And that can be a good solution when you're, for example, building a framework and you want to identify a specific user's request. You can generate a request ID, put it in a ThreadLocal, and that thread throughout the entire system will remember that value, and another thread will have another value, but you can model it in the same field in Java. So for example, if I want to keep track of the announcements in my restaurant code example, I could generate an announcement ID using a ThreadLocal, like I do here on line 3, and this class will then generate a unique announcement ID local to each thread. So that way I could print an announcement ID regardless of where I am in my application, and it will be tied to the thread that is currently executing it. The way this works is each thread holds an implicit reference to the copy of a ThreadLocal variable as long as the thread is alive and the ThreadLocal instance is accessible. Now after the thread goes away, all of its copies of ThreadLocal instances are subject to garbage collection. So that only happens when the thread has finished, has terminated. And this is the way I would use it in my code. This is the waiter class, the waiter who announces the courses. I could there write some output to the system out and call announcement.get, like I do there on line 5. And the same thing in the chef class, and because these two methods are executed by the same thread, I will have matching announcement IDs if the same thread is applicable here. These lines were the ones I was talking about. So if you want to use ThreadLocals and you need a unique ID, for example, for the thread that you're currently using, then using a ThreadLocal is an elegant way. It avoids you having to pass it using method signatures. And like I said, you can bind data that is unique to the current thread very easily. But ThreadLocals also have a few drawbacks. They are always mutable, so any part of the code that has access to your ThreadLocal that can call get on it can also call set on it. Secondly, it has an unbounded lifetime. So that means that ThreadLocal variables retain their values until you specifically call remove on it. Well, everyone tends to forget to call remove, right? So that's not very handy. So then their lifetime is practically the same lifetime as the thread that they are used in. Well, the threads in our example, they terminated quite quickly, so the risk is quite low, but if threads live longer, then ThreadLocals also live longer in memory, especially with Java's classic thread and thread pooling. This can pose a significant risk. And they can also be memory intensive, thirdly, especially when you're using many threads or when you are spawning child threads from parent threads. Because if you start a new thread from the first thread, then the ThreadLocal variables will be copied from thread 1 to thread 2, meaning that there's redundant storage needed to make sure that ThreadLocals travel from parent threads to child threads. So that's also a bit of a risk. Yes, that was a very long introduction to the fact why Hanno likes concurrency. So why do I like this topic so much? Well, I'm very happy to be in a place, at my place of work, Info Support. They give me the chance to combine Java consultancy with teaching courses. One of the courses I teach at Info Support is called Concurrency in Java. So if you're after this talk, I could imagine after this talk you're like, I've heard enough about concurrency for my entire life. That's okay. But if you're like me and I've sparked your interest, feel free to check out this link because there's a lot more to tell about concurrency than I have the time for in these 50 minutes, or come see me afterwards, right? A lot more to tell, and so if you want to learn more, come see me. Now, the recent Java versions have published various concurrency additions that are super exciting, and I think will change the way we use the language in the next few years. So I wrote a few articles about, well, a lot of them, about new Java releases, and a lot of while I was doing research for these pieces, I discovered that a lot of new features were related to concurrency. So that's the reason why I like to do that. Yeah, I'm very passionate about Java in general. I like to mingle in the community. I'm both a Java champion and an Oracle ace. So using those titles, I can also, reach more people with the good news about Java concurrency features. So here's also my contact information. If you like the stuff I'm telling you or want to keep in touch, feel free to hit me up. That means that it's now time to get out of the train and see where we're currently at. And I think it's safe to say that virtual threads is our current station. It was made final in Java 21, so that means that we can safely use it in production for like 1.5 years now. Is there someone who has already used a few virtual threads in their work? Oh, that's a few of you, so that's our current station, that's safe to say. A quick refresher for people who have never heard of virtual threads. So a virtual thread is a lightweight thread implementation, and it doesn't have any explicit mapping to an operating system thread. And it's intended to run only a single task over its entire lifetime. The JVM then takes care of scheduling, and it will schedule the virtual thread to run on a carrier thread, and by carrier thread we mean a thread that is directly tied to operating system threads. I think a picture is better here. So classic threads, the ones that we're used to before Java 21, you can think of them as these blue circles right here. So this line of blue circles, classic thread. But starting from Java 21, we now call them platform threads to distinguish them from the virtual ones. Right, platform threads. If you create a platform thread in Java, then it will always result in an actual thread being created in the operating system, the green circles right here. So this is one of the reasons why creating a classic thread and disposing of it is quite an expensive operation. I mean, we're talking milliseconds, but still, that's expensive, right, in computing terms. If you create like 5,000 of them in Java, that will take some time, because the JVM has to talk to the OS libraries, vice versa. And also, each platform thread in Java allocates by default 1 megabyte of stack space. As you may know, a thread always has its own stack. It allocates 1 megabyte of stack space. So that also means that if you've got 8 gigabytes reserved for your Java processes, and you try to create as many platform threads as you want, this will probably stop adding more threads at around 8,000 threads, maybe a bit more, because that 8 gigabytes of RAM will then be filled by all these 1 megabytes of allocated stack space. In contrast, virtual threads don't get a one-on-one mapping with an OS thread. They are just a JVM concept right here. So there can be many more of them. And creating them is far cheaper because we don't have to go to the operating system. And also the stack 1 megabyte allocated part is also not applicable here because the stacks of virtual threads are actually garbage collected. They are saved in the heap. So that means that we can have millions of them if we want, because we don't get this 1 megabyte of reserved space. And this is also a cool thing. The JVM scheduler will then decide on what platform thread a virtual thread will eventually do their work. And that means that a platform thread can be held in memory that can be decided by the JVM scheduler, and 1 or 2 or 3 virtual threads may reuse an already created platform thread. You can kind of compare it to virtual memory, virtual threads, virtual memory. To simulate a lot of memory, an operating system maps a large virtual address space to a limited amount of RAM. And similarly, to simulate a lot of threads, the Java runtime maps a large number of virtual threads to a small number of operating system threads. Again, pictures say more than words. So if you think of platform threads, think of passenger trains. They can carry a lot of cargo or passengers, but they are expensive to make, to fabricate, and they are slow to start and slow to stop. I'm not the only one, the first one who came up with that analogy, by the way. If you really like the subject, read this book. It's a classic. Now, if platform threads are passenger trains, then what is a good analogy for virtual threads? Well, I think taxis, right? Relatively cheap to make, fast to start, fast to stop. Though probably in this traffic you won't get very far. By the way, the picture is generated by AI. Some of the cabs, the taxis, are the wrong way around. There are half taxis somewhere, if you find. Turns out that a picture of more than 100 yellow taxis was not, I could not find it. So thank you, Leonardo.ai. Let's see an example of how virtual threads can help concurrency in your application. When a platform thread performs I/O, like for example fetching database data or getting data from a network request, the platform thread will be blocked until the response comes in. So these red areas here, those are the areas where we are waiting for some results. And there is no possibility to submit any more work on the platform thread for that time. So it is blocked until the response has been received. If we would translate this to using virtual threads, the picture would become something like this. And you would see that the virtual thread at the left side displays the same kind of behavior as the platform thread we had before, because it blocks as well. But the good part of the story is that it doesn't really have any effect on the operating system threads, because the virtual thread only exists in the JVM, not outside of that. So that means that it could probably run on a carrier thread 1, and the second part could run on carrier thread 2. We don't have any control over that because the JVM schedules it. But these empty parts in between, they used to be taken up by areas that the thread was blocked. But in this new situation, the platform thread is freed up to do some other work. In theory, another virtual thread could be scheduled here on this empty part and this empty part here as well. So that means that virtual thread can increase the throughput of our applications. I was at a talk at DevOps Belgium last year, and the talk was by Gregor Hope, and Gregor Hope had a very good quote about it that I want to use here. He said, higher throughput is wider bridges, not faster cars. So you will not speed up your application just by substituting your platform thread for virtual threads, but you can increase your throughput. You can make sure that the bridges that the cars run on get wider, so you can have more cars at the same time. But the cars itself will not speed up. Okay, so what if you would want to use virtual threads in our restaurant domain? Well, with the ExecutorService interface, it's quite simple. We just replace this line. And now it is an executor service that uses virtual threads. And one thing you might notice here is that we don't have the option anymore to configure how many threads it uses. And this is deliberate because virtual threads are intended to use only a single task over their lifetime, to run a single task. So that means that it doesn't make sense to tell the executor service interface, hey, use 8 virtual threads or 12 or 16. It will decide for itself what is the optimum amount. In this case, we're submitting 3 tasks, so it will use 3 virtual threads. Then pros and cons again. Millions of threads can run. I already explained why platform threads are limited in number. This limitation is no longer there with virtual threads. So that means that this allows a thread per request style. That means we can freely create new virtual threads for each task we want to be executed concurrently. And we don't need to keep thread pools anymore. That's just an old thing that we don't need anymore with virtual threads. So don't pull your virtual threads because it's not necessary. Creating them and disposing of them is cheap and fast because we don't interface with the OS anymore here, at least not directly. We get better throughput, and this is especially noticeable when you have a high number of concurrent I/O-heavy tasks, because the blocking part is, of course, the most noticeable when you're waiting for I/O. Right? So if you've got a lot of I/O-heavy tasks, you will certainly see a dramatic improvement when you start to use virtual threads. I do have to give a little bit of a warning here, because virtual threads are not that suitable for long-running CPU-intensive workloads. It's not that they are slower than platform threads, that wouldn't make sense, but virtual threads have a bit more overhead, right? They have to be mounted onto a platform thread. They have to be unmounted. Each virtual thread object that is created, of course, also leads to extra garbage collection. You could have situations of multiplexing, meaning that many virtual threads could be competing for a smaller pool of platform threads. That creates scheduling overhead. And starvation could also be an issue. Starvation of other virtual threads that are scheduled on the same carrier thread, especially when the active virtual thread is running a long-running CPU-intensive task. So if you already know that there is a very computational intensive piece of code that you have to run, and you know it's going to take a while, it is probably better to just run it with platform threads, because they have to be active anyway, and you can make sure that you don't have the drawbacks of mounting and unmounting of virtual threads. So short-lived tasks that have a lot of I/O are the best fit for virtual threads. One of the drawbacks that used to be there was pin threads. That means then that whenever code is in a synchronized block, it is within the synchronized block not possible to unmount the virtual thread until the synchronized block finishes. But this drawback has been mitigated for a bit, because in Java 24, a solution for this was published in the JVM. So there are 2 things you can do to mitigate this drawback. Upgrade to Java 24 as fast as you can. And if you don't have the option, you could replace your synchronized block with a re-entrant lock or with countdown latches, because they don't have the drawback of pinned virtual threads. Okay, we mentioned a few drawbacks earlier, but now that virtual threads are available, what drawbacks are amplified and what drawbacks do we need to address? Well, I think it's this one. ExecutorService allows unrestricted patterns of concurrency. This was the one-way jump, right? The go-to statements, but then in concurrency land. So that means that if you've increased the number of threads because you're switching to virtual threads, this drawback will amplify. And of course, the memory intensity of ThreadLocals, because if your thread count increases, which is a logical thing for people who want to use virtual threads, then more ThreadLocals will be copied in theory. So is this the final concurrency station? Well, of course not, because the drawbacks that I mentioned are the exact reason why Java's concurrency journey is continuing. And now it's time to look at structured concurrency. Fourth preview in Java 24, so you have to pass the compiler option enable preview, right, to be able to work with it. And what problem were we trying to solve? Just to refresh your memories, there were a few problems here with executor service approach, and they all had to do with canceling work that is no longer needed, right? And actually, if we would think about it, if we would model this problem with a single thread, we wouldn't have any of the issues, right? Because in this case, our waiter is Elmo. The poor guy has to do all the waiting in the single thread example, and he'll be very busy. But he will announce the courses in exactly the right order. And if the first one fails, he will not even think of starting on the second or third one. So we're looking for a way to achieve this behavior, but then with multiple threads. And that is where structured concurrency comes in. It's an approach to concurrent programming that preserves the natural relationship between tasks and subtasks, which leads to more readable, maintainable, and reliable concurrent code. The term was first coined by Martin Sustrix in 2016. He worked on Go routines in the Go language. And the Kotlin language also has a similar concept called coroutines, and they also support structured concurrency. To create, to use a visual again, on the left side you see the one-way jump that is a sign of unstructured concurrency. Structured concurrency will branch off in a scope, that is the gray area that you see, and all tasks will complete before the scope ends. So if they have clear entry and exit points. This is a simple hierarchy, but you can build more complicated hierarchies if you want, as long as all the tasks return to the same point in the end when the scope is closed. So scope continues until all child threads have completed, and this results in a strict nesting of the lifetime of operations that also mirrors their syntactic nesting in the code, by the way, and a streamlined error and cancellation propagation. So this will improve reliability and observability in concurrent code. I think it is time to see that in action. So I have opened up my IDE. This is the project that we'll have on the final slide, the GitHub project, so you can play around with this code if you want. I'm first going to just start this demo. Currently, it's the single waiter example. So our poor waiter is still Elmo. He will wait all the tables. And this is what Elmo does. He talks to the chef to determine today's starter course. The chef says, Elmo asked me to pick a starter so that announcement number 1 can take place. I picked creamy tomato soup. And Elmo says, I've received a response from the chef. This will be our starter, creamy tomato soup. And the same thing happens for the main course, lasagna, and the dessert course, apple pie. And then we're done. And the announcements are all the same number because it uses the ThreadLocal, and this is a single thread example. Now let's replace it by a structured concurrency example. I'm using a class name here that doesn't exist yet, so let's create it. It implements our restaurant interface. That means I have to implement this method, announce menu. Let's create a few waiters, Grover, Zoe, and Rosita. And here we are starting up our scope in a try with resources block. We define a variable scope, new structured task scope dot shut down on failure. I think we can get rid of the diamond operator. Yes, we can. And if we use announce courses here, then the 3 waiters will announce the courses. We use the fork method of the structured task scope, forking those 3 tasks, and then we'll tell the scope to join, wait for everything to finish, and to throw any exception if it failed. And in the end, we can return a new multi-course meal that has starter.get, main.get, and dessert.get. The cool thing about the structured task scope API, the structured concurrency API, is that once we are past line 21, we can be sure that everything has succeeded. Because if one of these invocations fail, this method throw if failed, will throw an execution exception, and we will not even reach the final line. So that is a very, very handy property, because once we're here, we don't have to deal with any execution, any fault handling. And also, join means it will wait for all tasks to finish. So if we call get here, it will not be blocking. So if we reach this line, we already know that the result is there. Now, I'm going to run this example a few times, because like I said, each ingredient has a 5% chance that it's not there, and then it will throw an exception. So in this case, everything is successful. The 3 waiters announce the 3 courses, main, dessert, and starter, and there are different courses each time. I'll just have to run it until it goes wrong. We're in luck, it already goes wrong. So it looks like we are completely out of raw beef. That means that we cannot serve carpaccio today. And the thing that I notice here is that the chef is picking all these dishes here, but not a single waiter here returns to announce it. And the reason for that is because the first invocation fails, the other 2 don't even get started, and even if they were started, they get cancelled. And this throws an exception, and we never get a multi-course meal. So that means that we have successfully implemented a cancellation policy here. And it was quite easy to do. Here's the code that we live coded just now. And this is the strategy that we call shutdown on failure. But there's a second strategy that I want to show you, at least on the slides. And this is the implementation of my story at the beginning of the talk. If the waiter lists all these kinds of drinks, but the first match is already successful, why should he continue listing it? Shutdown on success says, I'm starting up another structured task scope, but this one will shut down when something is successful. So that means that 2 waiters are asking for drinks, and they are listing all these categories, and if the preference of the guest is the same as the drink that they listed, this method will return get drink order, and it will be available through the result of scope.join.result, and a drink order will be returned. It's the exact same behavior, but it will shut down on success instead of on failure. You can also implement your own custom shutdown policies if you want, by extending the class structured task scope and implementing the handle complete method. Then you'll have full control over when the scope shuts down. Okay, now we've come to the section I like to call sanity checks. It contains a few questions that I imagine you may have after seeing this. So wait a minute. ExecutorService allowed me to pass a thread configuration. Can I do that with the structured concurrency API? Well, in a way you can, but it's meant to be used with virtual threads. So what you can do is call a structured task scope constructor and pass a different thread factory, a platform thread factory. And then if you would really want to, you can run it on platform threads. But it uses virtual threads by default. Why do we need all these scope classes? Why didn't they just enhance the ExecutorService interface to support it? Well, this is because the new class structured task scope imposes structure and order upon the concurrent operations. So it doesn't implement the ExecutorService interface because they are used in a non-structured way. So as you know, Java is a language that is very keen on keeping things backwards compatible. And this is the reason. So ExecutorService was not changed for a reason. However, I do expect that it will be straightforward to migrate code that uses ExecutorService. ExecutorService already supports invoke all, and CompletableFutures offers all off. Why would I need structured concurrency? So this is true. They both support this, but there are differences. ExecutorService and CompletableFutures do not support cancellation. So you can say invoke all or all off and wait for everything to finish, but you have to wait until everything has finished. It doesn't cancel anything. They can't create a task hierarchy. They cannot make the created task return to the same place and limit resource leak. They do not support custom shutdown policies. And they also don't support virtual threads by default. You can configure them to use them, but they are not the default. There's a more detailed comparison here if you would like. This slide, I'm not going to talk about it because it's full of content, but you could take a picture of it or go to the link that I put there. It's a comparison of various properties of ExecutorService, CompletableFutures, and structured concurrency, because there are three ways to do concurrency in Java, and they all have their own purpose and their own use cases, but they differ on a few properties here, such as chaining, error handling, timeout management. My slide deck will also be online, by the way, so if you didn't get to capture it right now, you could do it later. To summarize, virtual threads deliver an abundance of threads that are cheap to create and dispose of. Structured concurrency can correctly and robustly coordinate them. Scoped values, final subject for today. They are also in fourth preview in Java 24. What problem are we trying to solve here? Well, ThreadLocals. They are an elegant way to bind data that is unique to the current thread, but they are always mutable, have an unbounded lifetime, and are memory intensive, like we saw earlier. A scoped value is a better way to do a thread local. They are values unique to a thread that can be safely and efficiently shared to methods without using method parameters. They are immutable, you write them only once, and they can be read multiple times. They are comprehensible because they have a limited lifetime, which is made visible from the structure of the code. Again, they are robust. If you share data by a caller, they can only be retrieved by legitimate callees, and this is what they look like. You create a scoped value.new instance in line 1 there, and on line 4, you define a where block where you say, scope value in the field X is now set to hello, and then you run the run method if you provide a runnable, or the call method if you provide a callable, and the lambda expression that you provide there will be the scope of the scoped value. So that means that inside the method bar you can call x.get and it will print hello, but outside of the method bar that will result in an exception. So if we migrate our announcement ID to use scoped values, it could look something like this. And then we'll use here scoped value.where, announcement ID scoped value, and call this callable, which is the announce method. And for the entire announce method, we can call announcement ID.get, but not before that and not after that, because then we get an exception, because it's very specifically scoped. And also the chef method pick course that is called here also ends up in the scope. So we can also use announcement ID get here. So scoped values cannot be overwritten, but they can be rebound. Here's an example from one of the JEPs, JEP 446, that says we've got a scoped value X, we bind hello, and for the scope of that lambda, you can use it and it will yield hello. Then line 8 and line 10 will print hello, but in line 9 we rebind it to a new value, goodbye, with a new scope. So this is effectively a nested scope, and if we call it here, it will print goodbye. But on line 10, again, it will print hello, because that nested scope has terminated by then. Scoped values can also be inherited. This is a cool feature, because this is structured concurrency and scoped values working together. In this case, we are using the scope value drink order ID. We set it to the value of 1. And in this scope, because it's the lambda that we pass, drink order ID is available. But we are also forking 2 new threads here, of course, using a structured task scope. And the way this works is, by default, the scope will be extended to any threads that you spawn in a structured concurrency way. But this only works with structured concurrency because we can be sure that after the scope ends at line 17, all these tasks will have finished, and therefore the scope value, by definition, cannot leak outside of the structured concurrency construct here. So that's a very cool way that these 2 features work together. So are scoped values always a better choice than ThreadLocals if you use them right now? Maybe that's a question you have. I think you should migrate when your ThreadLocals deal with a one-way transmission of unchanging data. So if you're relying on resetting, so setting the ThreadLocals to different values, it might not be the best idea. Or if you expect to use many virtual threads, because then the risk will be higher. Don't migrate when your ThreadLocal is used in a two-way fashion. because scope values don't support that. Or you don't expect to use virtual threads, then the risk is not that high. Summarizing, thread locals don't limit mutability, perform badly with many virtual threads, and scoped values support immutable values, come with a strictly defined lifetime, and they can be inherited efficiently through structured concurrency. So how will this change your life as a Java developer in the next few years, months? If you're like me, a trainer or developer advocate, just try them out and talk about them, right? No restrictions. If you work on a framework or library, you can start using these features to enhance your product. Virtual thread is, however, the only feature that is currently finalized. So don't rely on them too much until they are final in Java. If you're a Spring developer, then you can use virtual threads by default using this method on the simple task executor. If you are used to Jakarta EE environments, you can use manage ExecutorServices and set virtual to true here in the annotation property for default virtual threads in your ExecutorService. And you can use the manage structured task scope way by passing a manage thread factory here. And then your AE container will know about the threads that are created there. If you're a Quarkus developer, you can use the run on virtual thread annotation to invoke the method that you annotated on a virtual thread. Have we come to journey's end? Is this the final station? Of course, the answer is still no. There are a few possible future features that were mentioned in the JEP. Sharing streams of data among threads, also known as channels. The language architects might propose to introduce that in the future. No guarantees, of course. And possibly a new thread cancellation mechanism, also mentioned in JEP 4.8.0. There is one future feature confirmed. And those are the improvements to the structured concurrency API. This is currently a JEP draft. It didn't make the cut for Java 24, so hopefully Java 25 will contain it. A few things are going to change. The basic mechanism is still the same, but the way you create structured task scopes will change probably in JDK 25. So in this case, line 9, we're using new structured task scopes, shutdown on failure. JDK 25, possibly, probably, you use a factory method called open. And by default, open will behave as a shutdown on failure. And also another difference, the throw if failed used to be mandatory. It is now optional, or to say it otherwise, the join method will immediately throw any exception instead of you having to type the second method. So that makes it a bit more robust. You could still, you can also do shutdown on success to show you how that works. Also the open method, but then you would have to pass a joiner that says any successful result or throw. And the good thing about that is that Java comes with a few predefined joiners that have a different behavior. And you can also overload the joiner here and pass it like a platform thread factory if you want, or a specific timeout. So lots of options to configure that. All handled in the joiner interface. It handles subtask completion, produces the result for the joiner method. This is what I was talking about earlier. These are the built-in joiners. Any successful or throw, all successful or throw, await all successful or throw, or until. So there's a lot more options to choose from if this JEP draft gets published. And you can also create your own, just like before. In this case, you would have to implement the joiner interface. I think we have time for 1 or 2 questions. And so if you have any, please feel free to ask. Yes?
So do you expect that structured concurrency will end up replacing libraries like RxJava and the like?
Yeah, so the question is, do you expect structured concurrency to replace RxJava kind of libraries, right? That is a good question and a good point. We started doing reactive things because platform threads were getting in our way a bit, right? It was expensive to create them and expensive to dispose of them. So it is an interesting topic. I mean, a lot of stuff that RxJava does can now be done with virtual threads, I think. So the need to use it is a bit less than before. So it all depends on whether the people at ArcsJava are going to use virtual threads themselves. If they are going to do that, then I can see them keeping the users they have. But if they don't do that, I would expect that the popularity will go down of the library. Personally, I wouldn't see the benefit right now. I wouldn't start a new project with ArcsJava, let's put it like that. But you could still maintain one if it still uses it. Yeah?
Thanks.
Final question, perhaps? Yes, in the back.
What happens if you don't call the join function?
What happens if you don't call the join function?
Yeah.
So then it will not wait in your main thread, they will not wait for the results to finish. So the threads will continue their work in the background, just like with ExecutorService. So that will not be structured concurrency, in my opinion. Okay, might be more questions. Come see me afterwards. For now, thank you so much for your attention. Enjoy your day.